All right, and like I said, this is a set of lectures on control volume analysis. We will designate this area or this volume as our control volume. I'm going to indicate control volumes that way. I guess the question for all is, do we have enough information to solve this problem? So what do you think? Do we know everything we need to know? These are circular pipes with this diameter. That's the cross-sectional average velocity at location 1. Do you think do we have everything we need to solve this particular problem? I see Casey in the back saying, yes, he thinks so. Ooh. Any other opinions? Yes or no? Which way you leaning? Exactly. It's like one of those professor questions that you think you'd say yes, but you ought to say no. Right. And the answer is no, that we are missing something. What we're missing is so the question is, this is say a manhole to a storm sewer, and it shows that there's water in the manhole. We don't know what's going on with the water level in the manhole. And it could be three possibilities. Could be constant. It could be going up. It could be going down. And given what we're given right now, there's really only one of these three possibilities that allows us to solve the problem. Doing the sorts of analyses that we've done previously, right? One of these would lead us to an answer. What do you think? Which water level going up or down? Do you think it's one of those? No, because what we also would need in that instance, we need more information on this manhole, maybe something about its diameter. If it's constant, then what we can say is that that the flow in is the flow out in that case. But in general, we need to know something about what's going on in the standpipe, the manhole. Another example that you might be more familiar with. I know this was back in the days when we had two little boys and they needed a bath. I would frequently, and it took forever to get the hot water going, and it was really busy. I would just open open the faucet, let the water run into the bathroom, and while at the same time I'd have the drain open so that the water level would slowly increase and get to the right temperature. And I'd just dash in there and adjust hot water or cold water until I got it right. So you can imagine that there's a Q in and a Q out, and a problem might be find the rate at which the water level in the bathtub is going up or down. I got an example like that later on, but we solve this, what we referred to previously as a continuity equation, but it's just a special case of a larger set of analyses. And just to say, if we look at all of the problems that we work, we generally have two methods of analyzing them. We look at a volume that's moving with the flow. And actually, I'll say that this lecture, if you're looking for the corresponding information in the text, it's some in chapter 4 and some in chapter 5. I'm not crazy about the order in which they present the topics in this class, so I'm not always just following it from the start of the book to the end of the book. And in this area in particular, I have to do a little from this chapter and a little from that chapter. So pardon me for that. But this is something that's in the chapter 4, what this term, a Lagrangian analysis. That is, you follow along with a volume that's moving with the flow. And that's opposed to you analyzing a volume fixed in space, which is called you think it would be Eulerian, but it's actually pronounced Eulerian. I believe the mathematician is Euler, E-U-L-E-R. So this is called a Eulerian analysis. And usually this is for our types of problems. This is the more practical way to do the analysis, is an Eulerian analysis. But as it turns out, this is closer to the basic physics. The basic physics that describe the problem. So we'd like to do it this way, but our basic physical principles are done this way, and we need some connection between the two. And there is a connection that's made with something called the Reynolds transport theorem. All right, so the Reynolds transport theorem, and let me show you that. I think when we end up with this discussion, we'll get to a point where we don't talk anymore about the Reynolds transport theorem, but we've got a little ways to go before we get there. So what is the Reynolds transport theorem? What it says is that and I was hemming and hawing as I was putting this up as it whether I should put a partial derivative or a total derivative here, and decided that none of these things, in the way that we're looking at it, none of these things in our analysis vary in space. We're looking at one particular point in space, and so it's okay to do it this way with not a partial derivative. Although I think in the text, maybe it has this one as a partial. It's not really that important. What is B? That's our property of interest. And it's what's called in the book an extensive property of interest. That is, it's something that varies depending on the amount of whatever it is you're talking about. So, so an example is if you were interested in the heat that's in a control volume, that's extensive. Because if you have something that's twice as big, it'll have twice as much heat at a particular temperature. So heat, yes, extensive, but temperature doesn't depend on the amount that you have. So temperature is not extensive. All right, and so what this says is that the amount of whatever in the system, however we want to define the system, is the time rate of change of whatever's happening in a control volume, and then the difference between what's leaving all right, and so to jump back to our particular problem, when we were talking the bathtub here, let's just leave the bathtub up and go over here. And I'm doing something that might be driving William crazy, because he has said he doesn't like the practical examples before we work through the before the basic theory, right? That was your, and I'm sort of jumping back and forth, trying to use the practical problem to sort of build our intuition about what we'd expect to find in the basic principles. So here's me jumping back to the practical problem. All right, so what you'd probably know just from being an experienced filler of bathtubs, that if the bathtub level is constant, then that tells you something about the inflow and the outflow, right? If the bathtub level is constant, then you know that, and can you get, and otherwise, if you're adding more water to the bathtub than it's draining out, you're expecting that the volume of the bathtub is increasing. Turns out that this is a special case of our Reynolds transport theorem, because say that B equals the, all right, so if we were to say do a mass balance, that's the extensive property of interest. This left-hand side, since we know you can't create mass, you can't destroy mass unless it's, some sort of nuclear sort of something, E equals mc squared, and it's not that. So we've got the left-hand side and in that case, when we're talking a mass balance in our control volume, it's always the difference between the rate at which mass is being transported in and minus the rate at which mass is being transported out. That's the Reynolds transport theorem that we are in general going to use. It's very much simpler to say that the time rate of change of the mass in the control volume is equal to, so this would be on the left-hand side, have dimensions of mass per time. It's just the difference between how much is coming in and how much is going out. And that simple version of the Reynolds transport theorem is going to handle every sort of problem that we do from now on. We're only going to be talking about, in this class, we only talk about the mass as the basic principle. Turns out we can actually come up with an even simpler version in many circumstances. So we're going to do an analysis that looks at a control volume. And here I'm just going to make a control volume. Locations 1 and 2. And in general, when we do this control volume analysis, we've got two questions that we need to ask. The first is our fluid incompressible, yes or no? And the second question is our problem steady, yes or no? And depending on how you answer that, you can, these two questions, there are four possible combinations. And I'd say that we do work some problems that in each of those four cases. And so I'm going to just go through the four cases and the version of the mass balance for a control volume that we would do in that circumstance. And then we'll work an example. All right, so this first case, I'll call it case A. Yes, it's incompressible. Yes, it's steady. This is by far our most common kind of problem. This is the problem we just had where bathtub in a, or water in a bathtub. And in that case, the equation that we use is the one that we know. Case B, we say, no, it's not compressible, but yes, it is steady. In that case, we do this. And if it's not compressible, then this density, and it's not necessarily equal to that density. So what we have is rho 1. Okay, so this might be in a control volume, the steady flow of water. This might be the steady flow of some sort of gas that can compress and change its density. And so, just to be clear, what we've got on each side is mass per time, which is mass per volume times a volume per time. That's the way we'll solve those problems. And then the last two cases, so yes, it's incompressible, but no, it's not steady. And we call this a a volume balance again, that was the one I showed you previously with the water in a bathtub. And then finally, the case where it's not incompressible. That's case C. And in this case, oops, and I guess I should say oops. All right, so you have three possible densities going on in this problem. There's the volume of our control volume and the density of whatever in the control volume, and then the flow and density of the stuff coming in minus the, the flow and density of the stuff going out. And those four cases cover all the possibilities of the problems that we'll have doing a control volume analysis. And now it's just a matter of doing some examples. All right. How are we doing time-wise? Oh, good, good, good. Okay, so I've got an example. And I suppose I should stop here and see if there are any questions. A good time to make sure there's nothing here that you don't understand, you might have a question about. Anything? We good? Anything on that? Okay, we're good. All right. So we have this above ground swimming pool with the surface area 400 square feet. It's raining at 2 inches per hour. And because of that, you're worried about the water level going up. And so you've opened an outlet. And the outlet flow is 20 gallons per minute. if H is the depth of water in the pool, which I guess we'll do in inches because I want to find dH dt in inches per hour. Okay, clearly there will be some unit conversions to do along the way. Now, so let's start off by saying which of our 4 cases do we think this is? You can look back through your notes and think, which case might this be? Look at the 2 questions. Looking for an answer from you. Which case is it? I have a C from William here. Cordell says incompressible, but not steady or constant. Yeah, so that's incompressible, not steady. That's case C. Incompressible, unsteady. I'm curious, did Cordell get his problem with his boss fixed? We had a conversation about that on Monday. He can just chat in an answer. And that might take a little bit, so not to derail it, but I'm interested. You can send me a message on that one. I'm curious.
He says yes and no, not more complicated.
Yes, these things often do. You get some, but not all of what you want. Okay, so in this case, where it's incompressible and unsteady, we're using this particular problem. So the time rate of change of the volume of the pool, which is going to be equal to the surface area times the time rate of change. We're just assuming that this has vertical sides on our above ground pool. So it has a constant surface area regardless of the water depth. That's equal to the flow in and the flow out. Let's calculate those flow in and flow out. I'm going to calculate them in cubic feet per second. So the flow in is the precipitation rate times the surface area of the pool. So there is rain falling on the water surface of the pool. Oh, okay, and while I'm here, say that Q out is the flow out that we're given in gallons per minute divided by 60 divided by 7.48 to get a Q out in cubic feet per second. We're also going to quantify this in cubic feet per second. Let's see, do we have, Liam, can you confirm my calculations there? I did them right before class. Or, okay, Kenna, you're doing as well? Okay, thank you. And then the trickier one is the inflow. I'm taking the inch per hour, dividing it by 12 to get it in feet per hour, and then dividing it by 3,600 to get it in feet per second. So, excuse me? Oh, did I mess? Oh, it's 2 inches, right? Yes, problem that I was playing around with the numbers to get it to work out to a reasonable value. That should be, yes, that says 1 there. Let's see, did I say? I did say 2 previously. 2 inches. Well, okay, let's go with this and see if it, so that's feet per second. The precipitation rate. And what do you get for that? Okay, that's what I want. Yes. Yes, so in the notes, yeah, I see it here. It says 112. It ought to be 212. I will fix that and re-upload the notes. Okay, and so there's our inflow and outflow, and then we can write an equation for dH dt by just taking this and moving the surface area over to the right-hand side. So I get squeezing it all onto this board, 6.5. I get that in the feet per second. That's not the unit that we asked for. So you want inches per hour. And then that's all right. And you get, oh, and I messed up one little thing to say this is actually a negative value, right? Because if we look, the outflow exceeds the inflow. So we think that the water depth is going down. So that should be a negative. And the water depth change in the units we'd asked for was, is that what you get, Liam? Yeah? Okay. All right. Oh, yeah, and it's negative. That is the, okay. And you could see that if we had no outflow, that it would be rising by 2 inches per hour. What we've done effectively is, and that's because of the precipitation is 2 inches per hour. What we've done is have an outflow that is effectively minus 4.8 inches per hour. We opened the valve a little more than we should have. And that's where I was going to end it for today. This is the sort of problem that you'd work on the next homework that hasn't been assigned yet. There's a couple additional control volume analyses types that we're going to do where we balance not volume, but instead momentum, and a final one for energy. So it's going to be control volume balances of mass and then momentum and then energy. That's what's on this upcoming homework. That's all for today.